it's a great pleasure to be here at Waterloo, the birthplace of so many of my friends in combinatorics. And I'm greatly honored to give this lecture in honor of Professor Tutte, whose work had greatly influenced all of us in numerous ways. My local host is Chris Gassel. We share a lot of common interest in spectral graph theory. So for a while, I was thinking that I will talk about some new methods for determining eigenvalues of graphs coming out from interactive games, among other things. And anything will have a lot to do with Tutte. In fact, characteristic polynomials is one of the polynomials that can be related to Tutte's polynomial. So I prepared all these talks weeks ago, and until yesterday. Yesterday, I was looking more and more into it, and so I made a rush decision of giving a brand new talk. Which I hope will fit the occasion better. And this piece of work is really connected with, I think, spirit of Tutte, I hope. And so I was looking at these games on graphs, right? And one of the famous graphs is the Tutte graph that we all know. It's a famous counterexample to the conjecture that all the bridgeless three-connected graphs, Hamiltonian, which serves as a counterexample. And this is one of the examples that bear Tutte's name. And there are many famous conjectures that I do not need to repeat too much, right? The famous flow conjectures, which remain open till today. Every bridgeless graph has a nowhere zero phi flow. Another conjecture is every bridgeless graph with no Peterson minor has a nowhere zero 4 flow. I don't think among many others. So there is another graph also bear Tutte's name. It's the 12th cage. It's also called Benson graph. So this is a less known conjecture related with Tutte's graph. The 12th cage is the smallest cubic graph with rectilinear crossing number 170. Conjecture made by Esso and Pegg. I figure more problems are good. And of course, we all know the top polynomial, which has many different definitions. In fact, being at Waterloo, I think I should mention matroid at least once. So this is once. And of course, graphs can be viewed as matroids. In fact, in all the talks will be about graphs. But basically, it's a nice way summing over all subsets of the edges. And there's a rank involved for the matroid, and so on. So there are many equivalent definitions for top polynomials for graphs. But my favorite one is the one that you can derive from deletion and contraction. So we have the top polynomial is equal to, deleting an edge or contracting an edge, if the edge is neither a bridge nor a loop. And there are these other inductive process. But the nice thing about this is that no matter which edge you pick, no matter what the order you pick the edges, you are going to get the same thing. It's an invariant. This is my favorite definition for polynomial. When we study type polynomial, a very natural question arises. That is the big question. What happened for directed graph? What is the appropriate analog? So we look into this problem. We come up with these polynomials. And that is what I want to talk about today, okay? So this started quite a few years ago at the Graph Theory Conference. We were trying to work on something. At the conference, you sort of shifted focus from your usual things. And so it led, at that time, for directed graph, what is the deletion contraction rules? And one natural rule is like this. If your edge E is not a loop, it goes from U to V, the deletion is very clear. You just kill it, okay? But the contraction is a bit different. This contracted edge sort of only have receiving and leaving, and it has to go in the right direction as E. So we use that as a definition. And this leads to, and what happens if it is a loop? So sort of this picture, you have to, the contraction sort of, you throw away that vertex that loop is at. So with this definition, which turns out to be a successful definition. So if we use this deletion contraction rules, again, the type polynomials are invariant in the sense that no matter how you pick your edge, you are going to end up with the same polynomial. Okay? So we were happily having our polynomials. And in fact, that later on was called cover polynomial for directed graph. After we wrote that paper, after a while, and it was picked up by Ira Gesso and people at MIT, Stanley, and so on. And later on led to a couple of PhD theses. And quite a few years later, we said, well, okay, came back to it again. So it's not too long ago, we started to have it all defined on matrices. Because if you can treat digraphs, then you'll have a very good chance to treat matrices. And also drop polynomial, which has a sort of a curious connection, actually came up when we were Ron was dealing with these juggling sequences, juggling patterns and so on. But of course, this drop is not dropping the ball there. It is more like drops in permutations, which I will explain. In fact, this will be what I will talk about. So the starting point is we really want to find an analog of type polynomial, but for directed graphs, right? So of course, this is not the only area that touch influence have been on my work. I view characteristic polynomials closely related with type polynomial as well. But I think we're not going to get into that today. So this whole thing started from a very, very special directed graph. One way to think about this is really a partially ordered set, okay? So if you have two arrows, then you close that triangle. That's a partially ordered set, right? Has a partial order there, post set. And suppose we have a bijection on, I put V there because eventually my space will be the set of vertices, okay? And so I think about it as a permutation of vertices. It's a bijection. Now, I can talk about drop at the vertex V. So what does that mean? It just means pi v is less than v. So this permutation make you go to some place which is going together with the order, okay? So in this case, we can clearly define drop. And we can talk about the number of permutations with k drops and use that Eulerian notation, p over k, okay? So if my p is very special, it is a chain, so it's totally or linearly ordered, okay, transitively closed. Then if it is a chain on n vertices, then we get Eulerian number. That was how I started to love Eulerian numbers. From there, I actually ended up having a joint paper with Knuth. He also loves Eulerian numbers. Usually, he tries to resist writing new papers because he has to focus on his volumes. But if you tell him about Eulerian numbers, he couldn't resist. So, and you get these numbers, 1, 4, 11, and so on, in the first row. Okay, so now we have a partial order set. And then we can define the incompatibility graph, which consists of all those pairs that they are not in any order, okay? So it is a well-defined, undirected graph. So we can talk about the chromatic binomial of this incompatibility graph. And that's a result of Goldman, Jaishi, White in 78 that has this beautiful expression. So the partial, so here are the drops, k drops, number of k drops, and together with this binomial coefficient, if you sum them up, then you get a chromatic binomial of the incompatibility graph. And this theorem has quite a few implications. This very beautiful theorem. So in the case that P is a chain, okay, on n vertices, then what happened? Its incompatibility graph are just isolated vertices. So you know exactly what the chromatic binomial is. And on the other side, that P over K turn out to be the Eulerian numbers. So you get this identity, which is the Wapitsky identity. Another way of using it is to set lambda to be -1. Then the left-hand side got simplified here, just the drop-free, the count of drop-free permutations. The other side, I should point out, this is using Stanley's famous theorem on acyclic orientation. So if you take a graph and take chromatic number and put -1, you get this number of acyclic orientation. And that is why if you put these two together, which is in this paper Brown together with Joe Buehler in '94, when they are dealing with all these juggling sequences and patterns and so on, it comes up. And they put those two together, number of drop-free permutations on P is equal to the number of acyclic orientations, dropping the S. Did all the view graphs midnight yesterday. Pretty sure we'll have typos, dropping an S there. So that was our starting point. So poset is a digraph. What about for general digraphs? right? A few things will come very natural. We can immediately consider permutations of vertices, and we can say for one permutations, how do we count the drop? The drop is just u pi u is an edge going there, okay? So the definition of drop is easy so far. And then we can have d over k, use the Eulerian number notation. It is the number of permutations with, on vertices with exactly k drops. And if the special case that we have transitive closure of a chain on n vertices, then we are back to Eulerian numbers, and back to Wapitsky and so on and so forth. So in fact, we are going to deal with, you can see transitive digraphs is like a partial poset. And they are simple graphs with loops allowed or acyclic, or allowing multiple edges, loops, and weighted. In fact, we are going to treat it all the way up, not just for simple graphs without loops, which makes better picture, but in order, it's sort of interesting to go up there actually. So here is one example. After the definition, always have an example. So we have one graph. That's the adjacency. That's adjacency matrix. You can see it's not symmetric. It's directed. And so here we have our count, right? 4 drops, 3 drop, 2 drop. So 8 permutations with 1 drop. Drop-free permutations, four of them for this particular graph. Now we can define drop polynomial of our directed graph. So we are choosing this form. So in theory, you can put them together with any power of x falling whatever. But that was particularly chosen, so we can go back to do things we want to do. Maybe we secretly work backwards. Anyway, this is the definition we put. Okay. And here are the drop polynomials for very small graphs. So here, they are really very small ones. The only sort of suspect is this one with a minus, because this is actually a convention. If you have 2 independent points, if you have k independent points, it's x k falling. And here they're a little bit bigger, but still pretty small, just on 2 points. So you can see it started to become more complicated when your graph gets bigger. It's using the deletion recursion, the deletion contraction formula, it's very easy to derive. And it's actually quite nice to prove any theorem. You can use, we use Maple, and really verify whatever you claim is true, at least for the cases you checked, giving you great confidence. Okay, so for this particular graph, for example, we use our numbers 2, 10, 8, and 4, and we get a polynomial. Okay, and I want to go back to deletion and contraction a little bit more. Because when you have multiple edges in these loops, it's actually interesting. So here, so previous picture that I did is a little bit oversimplified. Here, you really can see that, see, you use contraction, make a loop out of there, for example. And multiple loops, what happened? So, but anyway, all the papers are posted, so don't worry about the definitions too much. We tried many different ones. We ended up with one that actually worked for us. Like it is always been the way to be done. So here is the edge weight is 3. Has 3 edges in the same direction, for example. And here we have a deletion and a contraction. I think I put it here. At this point, it's not clear why do I put this one here. But in our paper, we actually do that with some special intention, which you can ignore. So we like to derive the sort of a contraction deletion rule for drop polynomial. Remember the previous deletion contraction definitions was given for cover polynomial, which just come from using the same kind of recurrence as top polynomial. Here we really have meanings which are drop polynomial. It turns out it's different, okay? Different from the cover polynomial. So that's why I was showing this again. So in order to really derive the contraction deletion rules for drop polynomial, then need a couple lemmas. If I have S edges from U to V, and one of these edges is denoted by E, then we get this contraction kind of relation. And there's a little bit more. So if I have S edges from U to V, and of course, S is greater than or equal to 1, one of the edges denoted by E, then there is such a reduction. So the drop number, K drops, is equal to, here you kill all S edges. Here you only kill, here you contract one edge. So there's a relationship. So all these small pieces about drop counts eventually comes back to the place we, okay, so put those together, then you get a recurrence for drop, the number of K drops for the digraph D versus you count drops in deletion and contraction. So you can see all these lemmas are geared toward the contraction deletion rule for drop polynomial. So here we sort of work in a different way from cover polynomial. Cover polynomial, the way we did is with contraction deletion rule and derive everything, and being so lucky, everything is working. Here we have a very clear definition about drops, right? And we want to say it satisfies contraction deletion rule. So that's all these lemmas are sort of pushing forward for. So this is the relationship, okay? Now, we can define drop polynomial, right? This is, actually, we define drop polynomial. This is just a reminder, right? All these drops, K drops coming out here. So we can now talk about drop polynomials for a digraph D. So it's satisfied. So finally, we have our theorem about contraction and deletion rules. So if there are S edges from U and V, and here U and V are not necessarily to be different, okay? And one of these edges is called E. then the drop polynomial for D is the drop polynomial of deletion plus contraction. But here I have to use something a little bit different. So that's the contraction deletion rule. And for the case it's 1, then we are back to pretty nice situation. Then there's a base case. What about an independent set? Because you do contraction and deletion, eventually you are going to reach somewhere. The somewhere is the independent set. So that's a base case, which is x n falling. The n falling is start with x and going down. And this is defined for all real x. Okay. We also have the situation when you have no vertex, so the trivial case, just to make everything consistent. And then it is just 1. So this actually is an alternative definition for the drop polynomial. And this one main proof is to show that they actually are equivalent. And here is an example. So you see we have our graph there. So it's another set of example. You see the polynomials coming out from contraction and deletion. Now, the next thing is that we move to weighted graph with real value weights. So it's no longer integer weights. Integer weights is like multiple edges, right, which we sort of deal with. But what about just real value weights? Again, we can define drop polynomial, right? So what it happens is that when you have a drop, I'm collecting all the weights and sum them up. So previously, we just count how many drops. And now, very naturally, it's a sum of edge weight on those drop edges. Well, what? And then we can define the drop polynomial here. Makes me slightly worried. Is that right? I hope I didn't. Okay. So anyway, so the weight is there, okay, over all permutations. So this definition is both simple and complicated at the same time, because over all permutations, there are a lot of permutations, right? In fact, we try not to compute that way, but it's a nice expression. That's why we have many theorems to say that's equivalent to many other things that allows us to compute. So here it says, for a weighted graph, the drop polynomial satisfies this, okay? So we have an edge, and it has an edge weight. When we do deletion, the deletion really means your weight dropped by 1 in this sense. So I'm not even call it deletion. I call it D prime. Don't know how to call it. It's not by removing it altogether. In the case the weight is 1, it is removing it altogether. But for the weighted case, it's just decrease the weight by 1. And that's consistent with the multiple edge situation. It's also decreased by 1. So it's more consistent with multiple edges situation rather than just deletion altogether. So this is not exactly called deletion, right? And the contraction is contraction. However, when you do contraction, you have to modify by its weight. So that's the contraction deletion rule for weighted digraph. And if we use that, then we are going to see it's invariant. It's invariant in the sense that no matter which edge you choose, it doesn't matter. You are going to get the same polynomial. And it's equivalent to the other definition we just gave. So it's sort of, there's a whole consistency with all the previous definitions, with our increasing families of graphs. So this leads to, I would say, sort of reciprocity theorem, right? So, which is in the similar spirit as, not exactly Wapitsky, but what happened is that we have a weighted digraph and we can talk about its dual. If it's 0, 1 weight, it's a real dual, right? The place of 1, you turn into 0. The place of 0, you turn into 1. So it's a real dual. So it's a duality kind of thing. And you know all commutatorists really love duality. So I guess not just restricted to commutatorists. In optimization, any area, love duality, right? So that's there. So here is the drop polynomial for the dual, okay? And here is the drop polynomial for the graph. But you have to change it a little bit, and you let the -1 to do miracles in the middle. So we have this reciprocity theorem, which we are very happy with at the end. So I think I sort of cover the drop polynomial pretty well so far, sort of skipping all the proofs, which is probably a good thing to do. After all, if you really want them, you know where to find them, right? So many remarks. We can define two-variable drop polynomial. After all, the top polynomial has two variables, has t, g, and x and y, right? We have a y there. So some cycle structure sort of coming out there. That y is always capture the cycle structure. So we sort of tried that definition. And in particular, of course, y is 1, that we go back to our drop polynomial. And this definition, it turns out it coincides with the cover polynomial for simple graphs. But if the graph is not simple, then there are tons of examples that they are different. Okay. And it's not too hard to see that the drop polynomial, to compute them, it is hard. It is in the same spirit as the top polynomial. We know that it is sharply hard, except for very special set of nodes, right? There's a famous theorem about by Jaeger, Vertonghen, and Welsh. There is a similar thing for cover polynomial. It's sharply hard, but only 3 exceptional points. So since for simple graph, cover polynomial is the same as drop polynomials. So we are sort of back to get a harness kind of situation. I want to say that we were trying to have the analog of top polynomial for digraphs. And we sort of capture some part of it. But as you know, top polynomials are so powerful, having so many wonderful applications and variations and relations with various invariants of graphs, together with knots, together with Potts model. And these polynomials, either the drop polynomial or the cover polynomial, capture a little bit flavor here and there, but is nowhere as versatile as the top polynomial for undirected graphs. So we are always in search of better polynomials. See, graphs is sort of like a two-dimensional kind of thing, at least two-dimensional. Polynomials is, you know, we all know polynomials. It's just a formula, right? If a polynomial can capture a lot of things about graphs, it is all power to you. So we always in search of better polynomials for digraphs, sort of leaving an open-ended question. Well, of course, one of the most famous work of Tutte is the chromatic binomials and golden ratio, right? That probably everyone here already know about it and know it well. So somehow for planar graphs, for triangulation of the two spheres is like plane, then you can talk about the chromatic binomial, which are really a way of counting proper colorings. So adjacent vertices will have different colors. The number of ways to properly color, which is the chromatic binomials all about. But the unbelievable thing is that you can really bound it here by this golden ratio to the powers here. So that's the formula. That's Tutte's paper, famous paper, 1970. So a couple weeks ago, maybe 2 months ago, I was at Berkeley visiting Simon's Institute, which is a relatively new institute, although the name is, say, on the theory of computing, but they have all these mathematical workshops, very close to what we are all doing. They have special workshops on algorithmic spectrograph theory, and then they had one, I was just there, on pseudo-randomness. So I was at Berkeley, so I went to a talk. See, that paper, Golden Ratio, is 1970, so that's almost 50 years ago. This paper is brand new on arXiv, and all I have is this arXiv version. I don't think it appeared yet, because mathematical papers always takes such a long time. So this paper by Argo and Krasko has a title, Tutte Relations, TQFT, which I don't quite know what it is. But it has a lot to do with that Q, which is quantum topological quantum field theory. I think that's why it is. In the planarity of cubic graphs. So it was mentioning the golden ratio, Tutte's results, several relations, and they try to generalize it and have a lot to do with these temporally leap algebra and topological quantum field theory. So the influence of Tutte is right there and it's still moving. And I have to say, I don't understand that much about that talk when I was there. I understand a little bit at the beginning, and but with this abstract, definitely, you know, will show up, right? I think there's still a lot to go there trying to find the right generalization. And it has more conjectures there. And with this, I'm finishing with my talk. So it is something like this, right? So there are always more problems. So thank you very much for your attention.
So do you know if Michelle Wax's chromatic quasi-symmetric function satisfies the same deletion contraction you have?
In fact, in our work, in addition to this paper, we did quite a bit of work on these so-called permutation statistics, which actually came out from this juggling paper. So we have sort of a new invariant, and for the juggling paper, it's sort of giving the new permutation statistics. And later on, I think that has some overlap with Michelle's work. So they are sort of coming out from the same source, but it is a little different here. I think they are really honestly doing drop and descents on graphs, on permutations, versus here we have an underlying graph.
Yeah, she has one on an underlying graph too, though, I think.
Okay, so they come from the same, source. So I won't be surprised. Yeah.
Any more questions? I have one question. Do you know what happens if instead of saying a drop in a digraph is just moving along one edge, you say a drop is moving anywhere along a directed path?
That I don't quite know. But the cover polynomials, really, if you look at the explicit formula for it, there are quite a few explicit formula without going through deletion and contraction. Then it has a lot to do with so-called path cycle cover. So you get a bunch of a union of vertex disjoint paths and cycles that cover every vertex. So over there, the paths coming out quite a bit. But if you just say instead of one step, you have to say how many steps, then I don't quite know. Yeah.
Are there any more questions? Okay, well, I'll mention, as always, that there is a reception right across the hall, starting right now, and I'll ask you to join me in thanking our speaker again.